Hello, all of you. At the onset of this class, let me share this lovely quote by Abraham Lincoln with you all. It says, "If I had 6 hours to chop down a tree, I would spend the first 4 hours sharpening the axe." Well, how beautifully this quote reflects the importance of spending time on preparation of a task before the actual execution. Well, with that positive note, let us now move on to the class. A warm welcome all of you to this lecture series on structural and stereochemistry. The syllabus has been divided into 5 parts and there will be one video each for each part. So today's class will be on structural isomerism, that is part 1 of the series. But before we move on to today's class, I would like all of you to have a good idea of the syllabus. Let us move on to the next slide where I have tried to keep everything as a classification. Please have a look. Well, this slide will give you an overview of the entire syllabus. As you can see, isomerism is widely divided into two: structural isomerism and stereoisomerism. Now coming to structural isomerism, this is divided again into chain isomerism, position isomerism, functional group isomerism, CPF, and also an extension of these, Metamerism and Tautomerism. Now moving to the other side, stereoisomers can be divided into two: configurational isomerism and conformational isomerism. Configurational isomerism again can be divided into geometrical isomerism and optical isomerism. Geometrical isomerism can again be divided into cis-trans form of nomenclature and also EZ nomenclature. This is mainly due to the restricted rotation in carbon-carbon double bonds or cyclic compounds. Moving on to optical isomerism. This again can be of two types. The isomers can be classified as enantiomers and diastereomers. Well, here this isomerism is mainly because of the asymmetry of the molecule or presence of chiral carbon atom or non-superimposable mirror images. Conformation can also be existing in two major forms, chair form and the bot form. And here, this is mainly because of the free rotation of carbon-carbon sigma bond. So this is an overview of the entire syllabus. Now let us take a look at the structural isomerism in detail. Certain molecules will show same molecular formula, but then the properties would be different. The reason would be the structural formula need not be the same. So such isomers are called the structural isomers. The isomers have same molecular formula, but properties are different because of different structural formula. Different types of structural isomerisms are: 1. Chain isomerism, 2. Position isomerism, 3. Functional group isomerism. There are also Tautomerism and Metamerism coming under this title. Well, chain isomerism. In order to understand chain isomerism, let us consider one example. Pentane. Pentane has 5 carbon atoms and 12 hydrogen atoms. It is a straight chain compound, CH3, CH2, 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 CH3. But then this can be represented as a 5 carbon straight chain or even a 4 carbon straight chain with a substituent carbon group, and also as a 3 carbon straight chain with 2 methyl substituents this. This is a pentane with 5 carbons on the straight chain. This is a butane with a methyl group as a substituent on the second carbon atom. We call it 2-methyl butane or isopentane. Now, this can also be a 3-carbon chain, that is a propane with 2 methyl groups on the middle carbon atom as substituent. That is 2,2-dimethyl propane. Well, here the major chain, the main chain of the compound is different and such isomerism, but still you may please note that the molecular formula is the same. So such compounds are called chain isomers because of the difference in the carbon-carbon chain. Now on to the next one, that is position isomerism. The compounds differ in the position of the functional group. They have the same molecular formula, same functional group, but different properties because they have different positions on which the functional groups are placed. Let us consider one example. C6H4Cl2. That is a dichlorobenzene with 2 chlorine atoms as functional groups. Now, where can we place these chlorine atoms on the benzene ring? Let us have a look. Well, the chlorine atoms can be on adjacent carbon atoms like this. We call it orthodichlorobenzene. It can be maximum distantly placed. We call it para-dichlorobenzene, that is 1,4-dichlorobenzene. It can even be 1,3 on this position, 1,3 dichlorobenzene, that is called a meta-dichlorobenzene. So likewise, the position of the functional groups are moving and that leads to positional isomerism. Let us have another example. Look at another example, that is C3H7Cl. This is a straight chain compound. It's a propane, chloropropane, C3H7Cl. Well, the chlorine can be on the first methyl group like this, 1 chloropropane. It can even be on the second methyl group like this, 2 chloropropane. So these two are examples of position isomerism. This slide shows yet another example of the same thing, that is pen-3-ol, pen-2-ol and pen-1-ol. What do you mean by that? It is a pentanol with the position of the OH groups changing. In the first case, it is on the third carbon atom. In the second case, it is on the second carbon atom. And in the third case, the functional group is on the first carbon atom. Pent-3-ol, pen-2-ol, pent-1-ol. This is yet another example of position isomerism. Now shall we move on to the next one, that is functional group isomerism. Now, what is functional group isomerism? We'll consider one example and try to explain that. Well, functional group isomerism, the isomers have the same molecular formula, but they have different functional groups. It is not the position of the functional group, it is a functional group itself that is different in both the isomers. In order for this isomerism to happen, definitely both the molecules should be having different isomers, but some kind of a similarity should be there in the functional group. For example, there will be combinations like alcohol-ether combination usually show such kind of isomerism. In this example that is cited, CH3CH2OH ethyl alcohol, on rearranging this becomes an ether, dimethyl ether, this compound. Dimethyl ether, alcohol ether is a typical combination that shows a functional group isomerism. Well, we have seen the first example, ethyl alcohol and dimethyl ether. Let us have a look at a few more examples. Here you can see the second example. It's a combination of acetone and propionaldehyde. Acetone is nothing but a ketone where you have the C double bond O keto group, which is a bivalent functional group. It has methyl groups on either side. That is an acetone. Just by rearranging it a bit, you get an acetaldehyde. The 2 of the CH3 is coming over here, and you get an acetaldehyde, propionaldehyde. It's a combination of ketone and aldehyde. Ketone-aldehyde combination usually gives you a functional group isomerism. Yet another combination is an acid-ester combination. Here we have an acetic acid and a methyl formate. Again, you can see how similar the molecular formula are, but then how different also it is. So these are a few combinations that you usually give functional group isomerism. That is alcohol ether combination, ketone aldehyde combination, acid ester combination. Well, an interesting example for functional group isomerism is a relation between a compound with a double bond and a cyclic compound. You can have a look here. 1-propene to cyclopropane. 1-propene and cyclopropane are functional group isomers. 1-propene has a double bond at the first carbon atom. And how can this be converted to a cyclic compound? When you convert that into a cyclic compound, we get a cyclopropane. So these two can also be considered as a functional group isomerism. An interesting example coming under functional group isomerism. Metamerism, as I said earlier, it's an extension of structural isomerism. Metamerism is the presence of same molecular formula, same functional groups, but the difference is in the type of alkyl groups placed on either side of the functional group. See, different alkyl groups present on either side of the functional group. Diethyl ketone and acetone with ethyl groups on either side. Its metamer will be methyl propyl ketone. That is a methyl group on one side and the propyl group on other side of an acetone group. Usually, the functional group has to be a polyvalent one so that it can have alkyl groups on either side. See this example, the example which we have seen. In the first case, pent 2-on, a methyl group on one side and a propyl group on the other side of the keto group. Whereas in the second case, we have just taken one methyl group to the left-hand side so that it is now evenly distributed. On the left-hand side, it is an ethyl group. On the right-hand side also, it is an ethyl group. So this is diethyl ketone. This is methyl propyl ketone. It is the alkyl group on either side of the functional group that are different, and such isomerism is called metamerism. Well, still another type of isomerism is tautomerism. Here, usually the isomers exist in pairs, and also there is rapid exchange happening between the two isomers, and also a dynamic equilibrium is established, is maintained between the two. Usual combinations are keto-enol isomerism and cyanide-isocyanide combination. Let us have a look at the keto-enol combination. Here you can see a ketone, C double bond O, a keto group. On either side, you can see methyl groups. Rapidly exchanging itself or transforming itself into an enol form. What is an enol? Enol is a compound with a double bond as well as an OH group, an alcohol functional group. So the ketone is rearranging itself. The double bond shifts to this position, and one of the hydrogen goes to the oxygen. So that is an alcohol in a compound with a double bond. Keto-enol isomerism. Another example is cyanide isocyanide rapidly changing to isocyanide. The difference is that here you can see hydrogen connected to carbon of the cyanide group. Here hydrogen connected to nitrogen of the isocyanide. Again, a dynamic equilibrium is established between the two. It's a typical case of tautomerism. Another type of structural isomerism is tautomerism. Here, the isomers exist in pairs, and there is rapid exchange happening between them, and also a dynamic equilibrium is established between the two. Popular examples are keto-enol tautomerism, cyanide, isocyanide tautomerism. We'll have a look at each one of them one by one. First of all, keto-enol isomerism. Keto compound, a ketone having two methyl groups on either side, that is acetone. This is going to rearrange itself to this form. What happens here? The double bond of the keto group is shifting to this position between these two carbon atoms, and one of the hydrogen atoms is going to the oxygen of the keto group. See here, that is what is happening, and this will result in a compound with a double bond as well as an alcohol functional group. Hence, we call it an enol. So this is a combination of keto-enol isomers which are in dynamic equilibrium and a rapid exchange happening between the two. The next example is a cyanide, hydrogen cyanide, rapidly exchanging to a hydrogen isocyanide. These two are also exhibiting tautomerism here. The difference is that hydrogen is connected to carbon of the cyanide group in the first example. Here hydrogen is connected to nitrogen of the isocyanide in the second example. So these two examples will tell you clearly what tautomerism is. With that, we come to the end of structural isomerism, and in the next class we will be seeing more on stereoisomers. Thank you.